Hello friends, myself Dr. Nandakumar Raugawale from College of Engineering Ambazugai is going to deal with Applied Thermodynamics 2. This is our fourth lecture. In previous lecture, we have discussed about limitations of reversed Carnot cycle, Bell-Coulomb cycle, that is reversed Brayton cycle or Joule cycle, coefficient of performance of Bell-Coulomb cycle working as a refrigeration system. And now today we are going to discuss numericals on air refrigeration system. So this is first problem which we are going to solve today. So the air refrigerator circulates 850 kg per hour of air. So that is nothing but mass flow rate of air is given. So MA. Through the cold storage chamber, there is a cold storage chamber through which air is circulated by this refrigeration system, where the temperature is 9 degrees Celsius. So temperature of cold storage chamber is 9 degrees Celsius, that we call as a temperature T1. Then the pressure is 1 bar. So here pressure P1 is 1 bar. The cold air drawn into compressor and compressed adiabatically. So index of compression gamma is equal to, we can take 1.4 because it is compressed adiabatically, to pressure of 5 bar. So here it is compressed to 5 bar, means P2 is 5 bar, and cooled at constant pressure to 32 degrees Celsius. So it is temperature T3, cooled at constant pressure, P is equal to C, to 32 degrees Celsius. Air is expanded to original pressure. What is original pressure again? It is P1. So original pressure means P1 is equal to 1 bar in the expansion cylinder, and finally admitted into cold storage chamber, and this cycle is repeated. So he is asking us to find out heat extracted in the cold chamber, heat rejected through condenser, coefficient of performance, and power required to drive plant, where specific heat at constant pressure for air is given as 1.005 kilojoules per kg Kelvin, and specific heat at constant volume CV is 0.718 kilojoules per kg degree Kelvin. Now we will extract the data first. So in problem it is given that air circulates at 850 kilojoules per hour. So mass of air circulated is 850 kg per hour, where the temperature of cold chamber is 9 degrees Celsius. So if we take this as T1, so temperature is 9 degrees Celsius, that is nothing but 282 Kelvin. So pressure at inlet is 1 bar. So P1 is equal to P4. P1 is equal to P4 is equal to 1 bar. Then P2 is equal to P3. P2 is equal to P3, and that is 5 bar. So he is saying that it is compressed adiabatically to pressure of 5 bar. So P2 is 5 bar. P2 is 5 bar, and that is equal to P3. So temperature T3 is equal to 32 degrees Celsius. What he says, if we see here, and cooled at constant pressure to 32 degrees Celsius. Cooled at constant pressure to 32 degrees Celsius. So here from 2 to 3 it is cooled at constant pressure, and T3 is equal to 32 degrees Celsius, that is nothing but 305 Kelvin, and specific heat at constant pressure, specific heat at constant volume is given. Then he is asking us to find out, first thing is heat extracted from cold chamber. So where heat is extracted, so heat taken Q in from 4 to 1. So Q in is nothing but Q4 to 1. So Q in we have to find out. Then he is asking us to find out heat rejected through condenser. So here heat is rejected at constant pressure, Q out, that is nothing but Q23. Q23 is Q out. Then work done, power required to run this refrigeration system, and coefficient of performance of this refrigeration system. So he is asking us coefficient of performance and power required to drive the plant. So now very first he is asking us to find out Q41 heat taken or heat absorbed. So here 4 to 1. So this is the constant pressure process. So we can find out Q is equal to mCp delta T. M is mass of air, Cp is specific heat, and T1 minus T4. T1 is higher temperature minus T4 is lower temperature. So here mass of air is given, Cp is given. So T1 and T4 we have to find out. So to find out T1 and T4, T1 is given, unknown is T4. To find out T4, so we have to use the correlation TP relations. T3 divided by T4 is equal to P3 divided by P4 to the power of gamma minus 1 divided by gamma. So what we know here is, we know T3. T3 is equal to 32 degrees Celsius or 305 degree Kelvin, and P3 is also known. P3 is 5 bar and P4 is 1 bar. Gamma is nothing but Cp divided by Cv. So we know everything, only unknown is T4. So from this we get T4, and when we substitute T4 in this first equation, we'll get heat rejected, heat absorbed by the refrigeration system. So this is how we'll get T4, and we'll get heat absorbed in kilojoules per hour, because mass flow rate is in kg per hour. Therefore heat absorbed will be in kilojoules per hour. If we are not taking this MA, then it will be in kilojoules per kg. So if we are writing this MA, this heat absorbed will be in kilojoules per hour, kilojoules per minute, kilojoules per second. Then he is asking us to find out heat rejected. So where heat is rejected during the process 2 to 3, which is this process, a constant pressure heat rejection process. So heat rejected in the constant pressure process is given by mCp delta T. So mass of air, specific heat of air, and T2 minus T3 kilojoules per hour. So what we know here is, we know T1, sorry, so we know T3, MA is known, Cp is known, T3 is known, T2 is not known. So to find out T2, again we use PVT relations. T2 divided by T1 is equal to T2 divided by P1 to the power of gamma minus 1 divided by gamma. So applying this PV relations to adiabatic process, PV raised to gamma is equal to constant for process 1 to 2. We can write T2 divided by T1 is equal to P2 divided by P1 to the power of gamma minus 1 divided by gamma. So this was the PVT relations applied to process 3 to 4. So now here what we know? We know P2, we know P1, we know T1. Only unknown is T2. So once we know T2, T3 is already known, we can find out Q2 to 3. So now here power is equal to work done in kilojoules per kg into mass flow rate in kg per hour. So if we use this without mass, then it will be in kilojoules per kg. Now here if we multiply it with mass flow rate, then it will be in kilojoules per hour. So here this work done can be obtained by Q out minus of Q in. Q out minus of Q in gives us work done in kilojoules per kg. So here power is equal to work done in kilojoules per kg into MA kg per hour. So this gives us power. So work done in kilojoules per second we can find out. So if we know this, actually what we have written while deriving, MA was taken as 1. So now here MA is present, means this MA is not required to be multiplied. So automatically this work done which we obtain will be in kilojoules per hour, and if we divide it by 3600 it will be in kilojoules per second, is it? So work done, power is equal to work done in kilojoules per kg into mass flow rate in kg per hour or kg per second. If we get then we will get power that is in kilojoules per second. But here MA is there. If MA is present, then we need not to multiply it by MA. So here to find out what we say Q4 to 1, we are using this formula, and Q2 to 3 we are using this formula. So already we are going to get it here by equation 1 and 2, this first part and second part. Directly we will get work done in kilojoules per hour. So that is divided by 3600 to convert it into kilojoules per second. Then COP is equal to refrigerating effect divided by work done. So refrigerating effect is nothing but heat absorbed, which is given by equation number 1, and work done which we are going to obtain here by equation number say 3, but this is in kilojoules per hour. So without dividing it by 3600, this work done has to be taken. So then we will get COP of refrigeration system. Now we will start to solve this problem. So now first of all we find out gamma. Gamma is equal to Cp divided by Cv. Cp is equal to 1.005 divided by Cv is equal to 0.718. So this works out as 1.3997, or approximately we call this as 1.4. Gamma is equal to 1.4. So first part we want to find out as heat rejected or heat extracted from cold chamber. Cold chamber. So this is given by Q4 to 1, which is equal to Cp or MA Cp T1 minus T4. This will be in kilojoules per hour. So if we do not take this MA, then it will be in, if it is Cp T1 minus T4, this will be in kilojoules per kg. So we are multiplying it by MA, therefore it will be in kilojoules per hour. So mass flow rate of air we know, Cp we know, T1 we know. To find out T4, to find out T4 we have to use this correlation, applying this PVT relations to process 3-4, because this process 3-4 is adiabatic process. PV raised to gamma is equal to constant. So applying this as T3 divided by T4, which is equal to P3 divided by P4 to the power of gamma minus 1 divided by gamma. So we know T3, we know P3, we know P2, we don't know only T4. So T4 is equal to, so transferring this T4 on right hand side, we get T3 divided by P3 divided by P4 to the power of gamma minus 1 divided by gamma. So substituting these terms, T3 is equal to 305 degree Kelvin, 305 whole divided by P3. P3 is nothing but 5 bar and P4 is 1 bar. 5 divided by 1 is 5 to the power of gamma minus 1 means 1.4 minus 1 divided by 1.4. So we simplify this. So this works out as 192.57 degree Kelvin. Sorry. Okay. So this is 192.57 degree Kelvin. So now MA value we know, this is 850, which is given in this problem. Mass flow rate is 850 kg per hour, into Cp is 1.005 into T1. T1 is 282 degree Kelvin minus T4, just now we have obtained as 192.57. So Q1 to 4 we get as 282 minus 192.57 into 1.005 into 850. So this as 76.39 kilojoules per hour. Q4 to 1. That is heat extracted or heat absorbed from cold chamber is 76.39 kilojoules per hour. Now coming to next term, heat rejected. Second term, heat rejected in condenser. Which is given by Q2 to 3. So heat is rejected in this condenser from Q2 to 3. Q out, which is given by MA Cp T2 minus T3. So we know here T3, we know MA, we know Cp. So what is not known to us is T2. So to find out T2, applying this polytropic law to this process 1, 2, PV raised to gamma is equal to constant. So here we write this as T2 divided by T1 is equal to T2 divided by P1 to the power of gamma minus 1 divided by gamma. So we know T1, we know P2, we know P1. So only T2 is unknown. So T2 is equal to P1, P2 minus P1 to the power of gamma minus 1 divided by gamma. So T1 value, which is known to us as T1 is 282 degree Kelvin. 282 degree Kelvin into P2 is 5 bar, P1 is 1 bar to the power of 1.4 minus of 1 divided by 1.4. So this works out as 446.63 Kelvin. So this is temperature T2. Now we can find out heat rejected. Mass flow rate MA is 850 into Cp is 1.005. T2 is obtained now 446.63 minus T3. T3 value, which is given in this problem as 305 degree Kelvin. 305 degree Kelvin. So 305. So if we simplify this as minus 305 into 1.005 into 850. this as 120.99 kilojoules per hour, because we are multiplying it by mass. If we are not multiplying it by mass, then it will be in kilojoules per kg, Q2 to 3. So this is how we obtained heat rejected. Now we want to find out the work done or power required to run this refrigeration system. Third bit which is asked here is power to drive. Power to drive plant. So work done. Generally we write work done is equal to Q23 minus Q41. This is nothing but Cp P2 minus P3 minus of Cp T1 minus T4. So this is work done. Now to find out power, if we multiply it by mass flow rate of air, so power is nothing but MA into Cp T2 minus T3 minus Cp T1 minus T4. This gives us power in kilojoules per hour. So this will be in kilojoules per hour. So this was in kilojoules per kg, because we have multiplied by MA. So this becomes kilojoules per hour. So how it becomes? Kilojoules per kg into kg per hour. Kg gets cancelled. Kilojoules per hour is the unit of power. So here to convert this into kilojoules per second, so this is to be multiplied mass flow rate MA. Now we just take it into the bracket. So this we take into the bracket. We write this as MA Cp T2 minus T3 minus of MA Cp T1 minus T4. So this is in kilojoules per hour, and if we divide it by 3600, then it will be in kilojoules per second. So kilojoules per second. To convert this into kilojoules per hour to kilojoules per second, we are dividing it by 3600. Now if we see this as, this is nothing but the amount of heat absorbed, so sorry, heat rejected, Q out or Q23, which is equal to Q out, already we have calculated, and this term, second term, is Q in, that is Q4 to 1, which is equal to Q in. So these two things already we have determined. So this Q4 to 1, Q4 to 1 is 76.39, 76.39. So this is 76.39 kilojoules per hour. And Q2 to 3, just now we have obtained Q2 to 3 is 120.99 kilojoules per hour. 120.99 kilojoules per hour. So here 120.99 minus of 76.39 into 1 divided by 3600. This will be 120.99 minus 76.39 divided by 120.99 minus 76.39 divided by 1600. This will be 0.01238 kilojoules per second, or this can be called as 1.01238 kilowatt. So this is how we obtained the power required. So just if we are taking mass flow rate, then it will be in kilojoules per unit time. So this unit time has to be converted into kilojoules per second, then it will be power in kilowatt. Now last thing which is remaining with us is fourth term, that is coefficient of performance. That is COP, refrigerating effect. Divided by work done. So now refrigerating effect, which is known as Q421, divided by work done is Q23 minus of Q41. So this we know, it was 120.99 kilojoules per hour, and this was 76.39 kilojoules per hour. So Q421 is 76.39 divided by 120.99 minus 76.39. So on simplification, we get coefficient of performance as 6.39 divided by 120 minus 76.39, 1.71. Coefficient of performance is 1.71 CU. So this is how we obtain the solution for the given problem. Now we will move to this next problem. So in this problem, what it says, a refrigerator operates between pressure limits of 1 bar, P1 is 1 bar and P2 is 8 bar. On a reverse Joule cycle, air enters the compressor at T1 is equal to 6.7 degrees Celsius and enters the expander turbine at 26.7 degrees Celsius, that is T3. Enters the expander turbine means expansion device. The compression and expansion follow the law. PV raised to 1.35 means N is equal to 1.35. It is going to follow polytropic process. Compute the coefficient of performance, specific power required in kilowatt per ton of refrigeration, and if flow rate of air, mass flow rate of air, that is given here is 6 kg per minute. In previous problem it was given in kg per hour. So Cp is given, Cv is given as that of in previous problem. So now we will collect this information in a table. So here P1, just see here, the air refrigerator operates between pressure P1 and 1 bar and 8 bar. So here P1 is 1 bar and P2 is equal to P3 is equal to 8 bar, P1 is equal to P4 is equal to 1 bar. So again P2 is equal to P3 is equal to 8 bar. So these two things which are given. So air enters the compressor at 6.7 degrees Celsius. So temperature at point 1 P1 is equal to 6.7 degrees Celsius, which is 279 degree Kelvin, and it enters the expander turbine at 26.7 degrees Celsius. So T3. So this is the expansion process. It enters expander at point 3. P3 is equal to 26.7. Mass flow rate is given as 6 kg per minute. So which is given here, 6 kg per minute, and N value is given. So because he is going to say that the compression and expansion follows the law of PV raised to 1.35, that is nothing but it follows the polytropic process. So he is asking us to find out the coefficient of performance and specific power required in kilowatt per ton of refrigeration. So here we want to find out COP first. So to find out COP, we need refrigerating effect divided by work done. That is nothing but to find out this, we must find out refrigerating effect. Refrigerating effect is nothing but Q41, and that can be obtained as Cp T1 minus T4. So Cp is given, T1 is given. To find out T4, we have to use this formula. T3 divided by T4, which is equal to P3 divided by P4 to the power of now N minus 1 divided by N, because this is following polytropic process, polytropic law. Therefore, P3 divided by P4 is equal to the power of N minus 1 divided by N. It is not a adiabatic compression. So P4 is known, we can find out Q1 to 4. Then to find out heat rejected, Q out, Q2 to 3, we can write as Cp T2 minus T3. So we know Cp, we know T3, we don't know T2. So to find out T2, again we have to use T2 divided by T1 is equal to P2 divided by P1 to the power of N minus 1 divided by N. So P2 is known, P1 is known, T1 is known, we can find out T2. So getting T2, by getting T2 we can find out this. Here we can get T4 from this, and substituting P4 in this equation we get refrigerating effect. So Q1 4 to 1 is known, Q2 to 3 is known. So we can find out work done. So work done can be given as Q23 minus Q41. So this gives us work done. So knowing this work done, Q2 to 3 is known, Q4 to 1 is known. So COP can be obtained. Or else this can again be obtained as specific power. Now power is nothing but work done per second. So work done in kilojoules per kg into mass flow rate, MA, in kg per second if we take, then we will get this as power. So once we get this power, and it will be in power will be in work done in kilojoules per second. So now we know 3.52 kilojoules per second is equal to 1 ton of refrigeration. So this we want in terms of kilowatt per ton of refrigeration. So if we divide it by 3.52, we will get it as specific power in kilowatt per ton of refrigeration. So dividing this by 3.52, we get specific power is equal to work done in kilojoules per second or kilowatt divided by 3.52 gives us work done in kilowatt per ton of refrigeration. So let us move to solve this problem. So first of all, we want to find out number one, heat absorbed is equal to Cp T1 minus T4. So Cp is known, T1 is known, T4 we want to find out. So therefore T3 divided by T4, applying polytropic law to this process, 3, 4, and you can write T3 divided by T4 is equal to P3 divided by P4 to the power of n minus 1 divided by n. So here T4 is equal to P3 divided by P3 divided by P4 to the power of n minus 1 divided by n. So T3 is known to us. It's T3 is 299.7 degree Kelvin. 299.7 divided by P3. P3 is 8 bar, P4 is 1 bar. 8 divided by 1 to the power of n value is 1.35 minus 1 divided by 1.35. So this is power, not in multiplication. So this, if we simplify, to 99.7 divided by 8 the power of so this is P4 is 174.804 degree Kelvin. So heat absorbed, that is nothing but Q4 to 1, which is equal to Cp value is 1.005 into T1 is nothing but 279.7 minus 174.804. So this works out as 105.42 kilojoules per kg, because we are not multiplying it by m, so therefore it will be in kilojoules per kg. So this is how we obtained Q4 to 1. Now we want to find out heat rejected. Number 2, heat rejected. Q23. This is Cp T2 minus T3. So we know T3, we know Cp, we don't know T2. To find out T2, T2 divided by T1 is equal to T2 divided by P1 to the power of n minus 1 divided by n. T2 is equal to T1 P2 divided by P1 to the power of n minus 1 divided by n. So P1 is nothing but 279.7 into P2 is 8 divided by P1 is 1 to the power of 1.35 minus 1 divided by 1.35. 279. This is 279. 279.7. 279.7 into 8 to the power of 479. 479.5 Kelvin. So Cp is 1.005 T2 is 479.5 minus T3. T3 is given as 299.7 Kelvin. So on simplification we get this as 180.74 kilojoules per kg, because we are not multiplying it with mass flow rate. So now we can find out the coefficient of performance COP, which is equal to refrigerating effect divided by work done. So refrigerating effect is nothing but Q41, work done is nothing but Q23 minus Q41. So this is refrigerating effect Q41, and this is heat rejected, that is Q23. So work done is given by Q23 minus Q41. So here Q41 we know, if we calculated Q41 as 105.42, 105.42 divided by Q23. Q23 is 180.74. 180.74 minus of Q14 is 105.42. So this works out as 105.42 divided by 180.74 minus 105.42 as 1.39. The COP of refrigeration system is 1.39. So now specific power is asked here. The specific power we want to find out. Fourth bit, specific power in kilowatt per ton of refrigeration. So here specific power, first of all work done. Now work done is given by Q23 minus Q41. This will be in kilojoules per kg. So Q23 we know. Q23 is 180.74 minus Q41 is 105.42. This is work done in kilojoules per kg. 180.74 minus 105.42. 75.32 kilojoules per kg. So here work done per minute, if we want to find out work done in kilojoules per kg into mass flow rate MA in kg per minute. So work done is known, 75.35 into mass flow rate of air is 6 kg. So which is given in this problem, 6 kg per minute into 6. So this works out as into 6, 451.92 kilojoules per minute, and if we divide it by 60, then it will be 7.532 kilojoules per second. So now this is power. Now we can call this as power in kilojoules per second or kilowatt. So we know the power that is nothing but 1 ton of refrigeration as 3.52 kilowatt of refrigeration is nothing but 1 ton of refrigeration. So specific power is equal to power in kilowatt divided by ton of refrigeration. So power in kilowatt is known 7.532 kilowatt, ton of refrigeration is 3.52. So on dividing this 3.52, we get it as 2.139 kilowatt per ton of refrigeration. This is specific power in this problem. So these are the answers which we obtained by solving second problem. In second problem, the law of compression and expansion are going to follow polytropic process. PV raised to 1.35 is equal to constant, PV raised to 1.35 is equal to constant. This is how we obtain the solution.